Okay, so we're continuing on with lesson 4 here, and we're going to talk about, we just finished talking about outliers, and now we're going to talk about what do you do if you have curved relationships. So remember that a correlation is only for a linear relationship, and a linear regression, a single linear regression, which is what we talked about in the last section, again, only deals with linear things or lines. So what do you do if you have a curved relationship? So let's say that you have a relationship that goes something like this. Let's say that you find points that fit something like that. So this line, the line that best fits these data, which is not a line at all, in fact, it's a curve, right? And a curve that looks like this. Right? If you try to fit a line to that, the best fitting line you could fit to that would maybe look something like that, which is not good here and not good here. It's just you can't fit a good line to it, right? So what do you do in this type of situation? And there are essentially, you have three options. If you have a curved relationship that's not linear and you want to do a correlation or regression, you have three options. One is you can transform your data. Two, and we'll talk about these in a second, I'll just list them up here so we can have them for reference, is that you can rank your data. You can rank transform your data. And three, so you can use a logistic regression. So instead of a linear regression, logistic regression there. So instead of a linear regression, use a logistic. So we'll talk about these in detail. So, all right, first of all, let's talk about transforming your data. So if you actually have a relationship that looks like this, this or anything that has a shape, I'll just draw it here and erase this. So if you have a shape that looks like this, this is exponential growth. You can see this commonly, for example, in animal populations or plant populations, which is that this is anything that grows not by a set adding of a number, but you add a certain percent to the population every year. So, for example, if you were, say, measuring, let's say, a kestrel population, and let's say that in year, this is the year, and this is the population size. That's population, right? Population size. Let's say you start off in year 1 and you have 100 kestrels. If you're growing by 10% a year, in year 2 what you'll have is, right, you'll have 10% of 100, which is 110. Well, you have 10% more, and that's growing by 10%, right? In year 3, you'll have 121, right? So this one you grew by 10, now you grew by 11. In year 4, right, you're going to grow by about 12, so now you're going to have 133. In year 5, now you're growing by 13, right? 10% of 133, so now you're going to have 146. Now you're going at 15 per year. Right, so now you're going to have 161. Now you're growing by 16 per year, right? 10%. So now you're going to have 177. Right, and you see what's happening here, right? Is that we're growing by 10% a year, but growing by a percent per year means that you're multiplying by a percent, and that means that you're actually on an addition basis. You're growing on what looks like this. So if you have data that looks exponential, so this is called exponential growth, what you want to do is you want to take the logarithm of this. And if you take the logarithm of this, you actually get a straight line. So what do I mean? Is that you literally take your data and you say, here you're going to add another, so in your Excel sheet or whatever you're working in, you're literally going to add another column and you're going to say log of population. and if you take, I'm going to say log base 10 of this population, and what you'll find is that what's a log base 10 of 100 is 2. Log base 110, log base 10 of 110 is, I believe, 2.04. Log base of 121, you can try this in Excel and you'll get 2.08. You get 2.12. Here you get 2.16. You get 2.20 about, and then here you get 2.24. So what you see is that if you take the logarithm of exponential growth, and if you were to plot this out, here you can see you're growing by 0.04 of the log of the population size every year. So that actually turns this relationship from an exponentially growing one into what would turn out to be, in fact, a linear one. So this would actually, if you log transform this, the relationship would actually look like this. Right? So it's transforming your data is perfectly legitimate. It's a bit of an art knowing how to, looking at your data to understand how you should transform it in order to make it look okay. Other common transformations, so log is a very common one. So if you transform it, the common ones are you can log, you can square root. These tend to be the most commonly used ones, but really you can do anything you want to this to try to make it look linear. Now the key here is that you have to remember that what you've done is that you've now effectively, so if we're looking at this kestrel population, remember what a linear regression is. What's a linear regression is that you have, let's do it in red, I'll do it in blue here, right, is that you're writing an equation where you're saying y equals a plus bx, b times x, and y here, right, is, for this size, we have, this is population size, and this is year, and for this graph down here, this is still year, but this is now log population size. Right, so in fact, let's draw these in different colors. So when you have, for the relationship, here, if you were to try to describe this with linear, it would be y is a plus bx. This would be a really bad line that wouldn't fit. But what you're doing here, right, so that line would, remember, it would look like this, not a good fit. But what you would, what here you're doing is you're saying literally this is population size, and this is year, right? X is year. So you're predicting the population size based on the year. Down here, what you're actually doing, you still have the equation, right? There's still linear regression. But now what you're doing, and this is still year, right? The x-axis is still year. Let's make a better arrow there. Right? This is year and this is year. The x-axis hasn't changed. What has changed is the y-axis, right? This is not, y is no longer population size. It's the log population size. So that means that the slope here means that for every, so here, this line would be in 1 year you grow this many animals, right? You grow by this population size. In this one, it's for every year you grow by this much of log population size, right? So this much for every year you grow by 0.04 log 10 population size, which to actually make that number you can interpret biologically, you would then have to take 2.04, take the opposite of a log 10. So remember to take the opposite of a log, right, is that you take it to the 10th power. So what this means is that you can take for this number, show us in blue, right, this, you take 10 to 2.04, it's going to equal 121. Right, you take 10 to the power, right? And this 10 to the 2.08 equals 133. Right, so what you have to reverse transform it to actually make these, when you're talking about this linear regression line, you have to reverse transform your transformation back to the original to actually have it make biological sense. Okay, I'm going to stop there and then we'll go on to the next two.